Okay, well, good morning, and thank you for the opportunity to come. I've been to Princeton a few times. This is my first time visiting the Institute, and it's been a great time so far. Todd, you're late. But it is a great pleasure to be here. So what I'd like to do today is tell you about some of the advances that I think are right at hand through the confluence of several large data sets from Gaia, from the Sloan Digital Sky Survey, from TESS, combining different types of data, astrometric, photometric, spectroscopic, that will allow us to make exquisitely precise measurements of the fundamental physical properties of lots and lots and lots of stars across the Milky Way, across the Hertzsprung-Russell diagram, and thereby enable us to address a variety of stellar astrophysics questions, which is to say, questions about the stars themselves, as well as questions about the things that orbit the stars, such as planets, as well as questions about the environments that stars inhabit, the Milky Way, places that stars form, etc. So this is really going to be focused on the stars. You're going to hear a lot about stellar radii. I'm particularly excited about the ability to make exquisite stellar radius measurements. And what I'm going to try to do is highlight for you some of the recent advances that have already occurred as a result of these approaches and data sets, and give a sense of some of the advances that are soon to come. Okay? All right. Oops. Okay. So let me start by, there we go. Let me start by sharing with you a couple of examples of exquisite measurements of fundamental physical properties of stars, done the what I'm now going to refer to as the old-fashioned way, which is to say one star, or actually two stars at a time, via what have long been the gold standards for stellar astrophysics, eclipsing binary star systems. And I'm going to give you a couple of examples that my team and I have worked on because, in part, because we spent a lot of time working on these systems before we entered this sort of data-intensive era. But these also give me an opportunity to give a sense of the rich astrophysics that can come out of detailed understanding of the physical properties of stars. So to remind you, one thing that makes eclipsing binaries so valuable for stellar astrophysics is that we basically are able to directly measure all of these fundamental physical properties of the two stars in the one system simultaneously. We don't need to invoke a distance. The underlying physics is quite simple and well understood. There are few theoretical assumptions. And so these are very direct empirical sort of laboratories. So here is one example eclipsing binary system that I worked on some years ago. This remains one of the eclipsing binaries for which the physical properties, in particular the masses and the radii of the two stars, have been determined most accurately. And so this is actually a young eclipsing binary star system at an age of just 1 or 2 million years. But you see what's possible through the combination of precise radial velocity measurements, light curve measurements of the eclipses at multiple wavelengths. In order to get to this level of accuracy in the masses and radii, you have to do some clever things. So for example, there's clearly a spot modulation signal in the light curve. Those spots can introduce radial velocity variations, but you can simultaneously model that, and through a global solution, you can actually account for the spot signature both in the light curves in the eclipse model and in the radial velocity orbital solution. And in the end, you end up with these phenomenally precise fundamental measurements. And so with that, then we can start to ask, to what extent do standard models of stellar evolution, in this case models of pre-main sequence stellar evolution, accurately predict the measured properties of a system like this. So in this particular case, we believe that the system has an age of a few million years because it's in a young star-forming region. We know the masses of the two stars to be about 1.0 and 0.7 solar masses. We've measured those masses. But here is where the two stars are in the HR diagram with error ellipses around them. And these are two popular flavors of pre-main sequence stellar evolutionary models. And so one thing that we can glean from this is that the treatment of convection in the stellar interior is important. So this is a standard mixing length theory, sort of alpha parameter for convection in the interior. And in this case, with a solar-like mixing length alpha of 1.9, these models are able to just about reproduce the position of the more massive star in the system, but completely miss the lower mass secondary. Whereas if we go to a much lower mixing length alpha, which is to say less efficient convective mixing in the interior, we do much better. So we can begin to suss out something about the physics of the interiors of these stars through these comparisons with models. And then in a detailed case study like the one that I'm showing you, we can even go further and say, what might we learn if we also take a look at the chemical abundances of the stars? So I just told you that this model comparison that I showed you on the previous slide is suggesting that less efficient convective mixing in the stellar interior provides a better fit to the observations. Well, we also have measurements of the surface lithium abundances of these stars. Lithium, stars form with a sort of primordial lithium abundance of 3.3 on this scale, but lithium gets burned at low temperatures early in a star's life, and so surface lithium abundance steadily declines over time, and it provides another kind of a clock on the one hand, but it also tells us something about the efficiency of mixing in the interior. And so here are the observed lithium abundances for the two stars in this same one eclipsing binary system, the higher mass star and the lower mass star. And these are models. Remember, the higher mass star has a mass of exactly 1 solar mass, give or take 1%. Here are models of the surface lithium abundance with time for a 1 solar mass star during the pre-main sequence evolution. Here's the nominal age of the system. And you see that the efficiency of interior mixing has a very, very strong effect on how rapidly the surface lithium abundance gets depleted. And so here again we have a kind of a triangulation on this conclusion that the modest amount of depletion of surface lithium abundance in the 1 solar mass star in the system is most consistent with relatively inefficient internal mixing. If the star had solar-like internal mixing, its lithium abundance would be way down here. Okay? So that is one story about two stars in one system. We've learned a lot. Here's another one. This is a system that at the time was exciting to discover. It was the first ever known eclipsing binary system consisting of two brown dwarfs. 12 years later, it is the only system known of two brown dwarfs in an eclipsing binary. And so it actually has turned out to be and remains a really useful sort of benchmark for understanding very, very low mass stellar and substellar object physics. This is, again, a young system. Both of the eclipsing binaries that I'm talking about here at the beginning came out of a focus survey of a star-forming region. So these are young systems. And so if it seems surprising to you that the objects in this eclipsing binary system have masses of like 60 and 40 Jupiters, yet have radii of 1/2 to 2/3 of the sun, that's because these are extremely young brown dwarfs, very early in their gravitational contraction, and so they're big. We did a bunch of follow-up to confirm that it's a relatively clean system. There's no circumstellar disk. There's no accretion going on. And one of the early surprises is that whereas any standard evolutionary model for these things would predict the usual monotonic relationships between mass and temperature, mass and radius, mass and luminosity, the more massive brown dwarf in this system is actually cooler than its lower mass companion. And quite a lot cooler. Yet the luminosities come out about right. So we thought that was curious. Come out in agreement. In agreement in two senses. One, that the more massive brown dwarf is the more luminous one. So at the most basic level, that monotonic relationship between mass and luminosity is obeyed. But also this particular flavor of evolutionary models makes a prediction for what the luminosities should be at this young age, and it's consistent. Those same models would predict a particular relationship in temperatures, and it's totally different. So we spent quite a lot of time chasing after this, and we did some long-term follow-up. One of my graduate students was able to measure out the two brown dwarfs' rotation periods through long-term photometric monitoring. We also were able to measure chromospheric H-alpha emission from the two brown dwarfs. I love this picture. This is the H-alpha line, the nebular H-alpha emission from the Orion H2 star-forming region in which these two brown dwarfs are embedded. And you'd never be able to pick out the little H-alpha emission from the brown dwarfs in there, but thankfully they're whipping around one another, and as they Doppler shift, shoop, we're able to pick it out in the wings of the nebular line, and then it comes the other way, shoop, and we get a second try. And so it turns out that the more massive brown dwarf, the one that is cooler than it's supposed to be, is also spinning quite fast. And we can measure its H-alpha luminosity. It's very, very large compared to its bolometric luminosity. If you apply some standard relations for chromospheric H-alpha emission to some nominal field strength, you would infer a field strength on the more massive brown dwarf of several kilogauss. The point is just that the more massive brown dwarf is definitively spinning fast. It is chromospherically active, very chromospherically active, presumably because it's spinning fast. And it has this funny property that the temperature is sort of all wrong. The lower mass brown dwarf is spinning slow. There's no detectable chromospheric emission. And so we started to wonder if maybe something about the magnetism of the more massive brown dwarf is implicated in the screwed up physical properties of it. So here I'm showing you the two brown dwarfs now in an HR diagram. This is a nominal 1 million year isochrone for this system, a particular choice of pre-main sequence isochrones. The point here is just to say that, again, remember, we've measured the masses of the two brown dwarfs. We know the masses, 60 and 39 Jupiters. Okay. We also measure the temperatures of the two brown dwarfs. You see the more massive brown dwarf is quite a lot cooler. All right. The lower mass brown dwarf, at least with respect to this particular set of models, is at the quote-unquote the right place in the HR diagram. This is where this particular set of models would expect that lower mass brown dwarf to be in temperature and luminosity, and it's just about where it should be. This is a typical error bar. This guy is in the wrong place. Interestingly, if you didn't know the masses of the brown dwarfs, we know the masses of brown dwarfs, but if you didn't know, and you were to have observed this brown dwarf in the field, and you were to measure its temperature, and then you were to use some model to infer the mass of that brown dwarf on the basis of its temperature, say you didn't have a good measure on its luminosity or distance, you would get you would infer a mass that was a factor of 2 smaller than the actual mass. So there's an effect, there's a really important effect on the inferred bulk properties of these things. But
the temperature effect is coming from luminosity and radius, or
from the spectrum. So we measure, in this case, we measure this. And we also have measured the masses, right? So we went a step further, and we said, all right, at this time, there had come to be known a number of low-mass star, not brown dwarf, but in any case, low-mass stellar eclipsing binaries. And so we developed just an empirical relationship from this population of low-mass eclipsing binary stars. There's scatter, but the best fit relationships between the strength of the chromospheric H-alpha emission and the amount by which the star's temperature is cooler than you expect, and simultaneously its radius is larger than you expect, is shown by these best fit relations. And just to give you a sense of how this goes, at some nominal chromospheric emission level, say here, you have a temperature suppression factor of 5% and a radius inflation factor of like 10%. And so, right, temperature goes in like the fourth, radius goes in like the second power in the Stefan-Boltzmann relation. And so this is how it can happen, that you can have the temperature be cooler than it would have otherwise been, and the radius be larger than others would have been, but the bolometric luminosity comes out about what you would have expected. So we then took those empirical relations, and we asked, if we take now the measured chromospheric emission of the more massive brown dwarf and ask, where would it have been in the HR diagram if it were not chromospherically active, just using those empirical relations that I just showed you, that's where it would have been. So now, to be clear, this is where the brown dwarf is in the HR diagram. This is just to say that's where it would have been, presumably, if not for this magnetic activity. So this gave us some confidence that there really is a relationship between the magnetism of these low-mass objects and bulk properties of the stars, their radii, their temperatures, and then, if you didn't know better, the masses that you would infer. So, okay, so I told you two stories of two eclipsing binary star systems. 4 stars, actually 2 stars and 2 brown dwarfs, in 2 systems. And we've learned a lot. Fast forward now, we can start to operate at a more, what's the word? Retail sort of scale of operation, right? Up until now, this kind of precision stellar astrophysics has been very boutique-y kind of work. But as we entered the era of Kepler and K2 and now coming up on TESS and Gaia, a number of us started thinking, well, how can we start leveraging the power of these eclipsing binary star systems, the handful that are known and very well studied, to sort of test and calibrate and bootstrap to these upcoming much larger samples. So let me start with this example of the Pleiades. You may know or remember that the Hipparcos mission, sort of the predecessor to Gaia of 20 years ago, and provided parallaxes for hundreds of thousands of stars, very important mission, got one answer notoriously wrong in its parallaxes, and in particular the distance to the Pleiades. That we know of. Actually, I'm going to give you some reassurance in a second that this is the only case where Hipparcos really got it wrong. But so here's the Hipparcos measurement to the Pleiades, significantly off from basically every other measurement. From the Kepler mission, from the K2 mission, we discovered a previously unknown eclipsing binary star system in the Pleiades. We performed the kind of analysis that I just showed you, but we turned the problem around and said, we know the radii of the 2 stars in this eclipsing binary. We know their temperatures. Therefore, we know their luminosities. We can add 2 luminosities together. We measure apparent magnitudes. We can derive a distance or an apparent parallax. And so this gave us a more recent, still other independent measure to the distance of the Pleiades. It agrees with the long distance of the Pleiades as with everybody else. Hipparcos got it wrong. But this really got us started thinking, well, just how accurately can we measure distances as we enter the Gaia era, right? I mean, Hipparchus got the answer, one important answer wrong. We should be at least on our toes with Gaia and have methods of independently testing the distances that Gaia gives us. So Willie Torres and I assembled all of the 100 published eclipsing binary systems that have been characterized to the level of a few percent in the fundamental properties. So let me just pause right there to say that decades of effort, painstaking boutique level operation has gotten us of order 10 to the 2 eclipsing binaries, twice that many individual stars in those binaries with these really, really precise properties. A lot of time, a lot of effort, not much yield. Nonetheless, we can leverage these. What I'm showing you here is something that seems so simple on the face of it, yet it would be easy to overlook sort of how much time and effort the community has had to invest in order to get to this point. These are spectral energy distributions for 6 example eclipsing binary star systems from our sample. Right? When we observe these eclipsing binary star systems photometrically in broadband colors, the 2 stars are just combined light. But we know the physical properties of the underlying 2 stars. We can add them together. And what you're seeing in each of these cases is a fit of 2 underlying stellar spectral energy distribution atmospheres with 1 free parameter, reddening. And you can see in some cases there's no reddening, and we fit the data beautifully. Here's a case of an enormous amount of reddening. This is a distant hot star system. But with the 1 free parameter, we can match the data extremely well. Yeah, so this is what you observe. And then you can ask, what would it have looked like if there weren't reddening in the way, and that's that. And the point is that we now have entered an area, and again, we take this for granted, but for large, large numbers of stars in the sky, we can now basically add up the bolometric flux by looking up catalog magnitudes of stars. Because we have Galax near UV fluxes, we have APAS and Sloan and Pan-stars optical fluxes, we have 2-mass near-IR fluxes, we have WISE mid-IR fluxes. And we actually did the experiment of asking, suppose we were to just literally add up these fluxes. For most stars, except for cases like this, for most stars like this, literally just adding up these fluxes gets you like 80% of the bolometric flux, just what's contained in these broadband passes. If you then were to just connect, just kind of dumbly connect these individual measurements with lines and integrate under that piecewise linear thing, you actually recover about 95% of the bolometric flux. And so in a sense, just by using simple stellar atmospheres, these are Caru's atmospheres, the atmosphere model provides a kind of intelligent interpolator so that you kind of get that last couple of percent on the bolometric flux. But this is really quite simple and very empirical by virtue of all of these broadband photometric measurements. That's a fair point. You do have to, in our case, we just assumed a standard R sub V. That could tweak things a little bit. It turns out to be at a pretty secondary level. Yeah. Yeah. It's at the 1 to 2% level. Well, so yeah. So now you have to take a step way back and ask about fundamental calibrators like Vega or something, or maybe even the sun. Actually, I'm not so sure, but some really, really fundamental calibrator, and ask, to what extent does the absolute flux calibration in these different systems, right, say Galax versus 2-mass, what are the systematic offsets there? And the offsets that I've seen, I haven't dug down to what the fundamental calibrators are, but the typical systematic offsets that I've seen quoted are at the level of 1 to 2%. So, but that's an opportunity to just say that we expect that a bolometric flux measured in this way, in this totally empirical way, can be done at the level of a couple of percent. Now, when you're trying to infer a distance to something, that bolometric flux actually goes in as the square root. So you actually gain back a factor of 2. So the bolometric flux actually turns out to never, in practice, be the limiting factor on the distance that you can infer. So what we did then was we used all of the eclipsing binaries in our sample. We had a master sample of 100 so. Most of them, but not all, had Hipparcos parallaxes. So Scott, this is just to show you that at least with this sample of eclipsing binaries spread out across the sky at distances ranging from 100 parsecs to a few kiloparsecs, these are just sort of sigma units here. There's maybe 1 or 2, 2 to 3 sigma outliers, but in this number of objects, you actually expect 1 or 2 of those. Everything agrees well within this Hipparcos set. So there's no evidence that among this sample and the parameter space that it spans, that Hipparcos got any other answers wrong. What really impressed me is the color coding here is the fraction of the bolometric flux that is from beyond the span of the observed flux measurements. So we have some cases of hot distant stars where even with GALEX, 90% of the flux is coming out blueward of the most blue flux measurement that you have, and yet everything works out. And I think it's just because, you know, we have a pretty solid understanding of how stars radiate. And so even when you find yourself extrapolating in a case like this, it's not a blind extrapolation. We have a pretty good understanding of what's going on. So we can use these calibrators, and so we then most recently applied those eclipsing binary calibrators to the Gaia DR2, the most recent Gaia parallaxes. And so now, you know, this is a nice test of whether you're a half glass full or half glass empty kind of person. We measure an offset, a systematic offset of about 80 micro arc seconds between the distances to these that we measure for these eclipsing binaries versus what Gaia DR2 reported. So if you're a glass half empty kind of person, you probably go, oh my goodness, there's a systematic error. If you're a glass half full kind of person, you would say, and this is what I would say, is that the Gaia team, in my opinion, has done a remarkably good job of characterizing the uncertainties, including the systematics. In the Gaia DR2 release, the Gaia team made it clear that they expected up to a 100 micro arc second systematic offset. And I would say we have confirmed that. Adrian?
Did you look at this as a function of distance?
Yeah.
The photometric, like the center, the photocenter will change at different amounts depending on how far away the eclipsing binary is.
Oh, wait, distance of what to what?
The distance of the eclipsing binary.
To Earth.
So they fit single cell.
Oh, you're saying that there could be photocenter motion. And if it's really far away, it'll be 0 photocenter motion. If it's really close, it'll be big. Well, so we did look at whether this offset appeared to depend on distance. With this sample, there was nothing obvious. I should also make clear these are Milky Way eclipsing binaries. We reach out to 1 or 2 kiloparsecs with this sample. So now since then, there have also been others. Joel Zinn and colleagues used an astroseismic sample. They get the same answer. Basically, they find 60 microarc seconds versus our 80. They span a bit of a larger range, and they found a hint of a distance dependence. Now, in that case, it wouldn't be because of photocenter motion, but just some scale issue. In any case, I would say, know about this offset. Congratulate the Gaia team for having been so meticulous and careful in their work. But we can actually now apply these corrections.
So the way
You could.
Absolutely. Or another way to phrase it is the scatter that one sees here, is that consistent with the errors that you would have thought a priori for your system?
So yes on that. As to sort of who's right and who's wrong, you know, you can get sort of philosophical on it. I would just say that, you know, as I showed you earlier, we were able to verify the consensus distance to the Pleiades using this methodology. And,
How that maps up the 80 microarc.
oh, well, but that was for Hipparcos. But the point being just that the methodology, I think, is robust. And we now have had our eclipsing binary sample, the Zinn et al. Astroseismic sample, the Rees et al. Cepheid sample, the somebody et al. Lyrae sample, the somebody else et al. Red clump sample, and the sense of the offset in all of those samples is the same. The exact answer ranges among those samples from 50 to 80 microarcseconds. So I think we got it right. Okay.
But are all these models
Yeah.
based on models are?
You mean the stellar atmosphere models? So, let's take that conversation offline. I'm worried that we could really go down a rabbit hole there. Anyway, so I wanted to just say that, you know, 10 years, you know, we're getting ready to enter the next decade, and where we were at the beginning of the current decade in terms of samples of stars, of benchmark quality, precise measurements in these various ways, you know, again, you know, credit to the many of us who have spent most of our careers so far on this kind of work. But look, let's face it, the numbers here have been quite small. And we're now entering this new era that I'm very excited about, because where Hipparcos gave us that region of the galaxy, and the first Gaia data release got us that region of the galaxy, by the end of the Gaia mission, we basically will have parallaxes and proper motions for, you know, if we were looking at the Milky Way from above, you know, this half of the galaxy. It's an incredible mapping expedition with, you know, microarcsecond precision. We also simultaneously, for some of this footprint, will have test light curves for within the full frame images of order 100 million stars with high cadence, you know, high-ish cadence, with good precision. So now we have time domain information. And then with the current and the next generation Sloan Digital Sky Survey spectroscopic surveys of order 10 million stars with high resolution near IR spectroscopy, the ability to do temperatures and surface gravities and detailed chemical abundances for millions of stars, we'll be able to really pull things together for very, very large samples. Okay, so let me now give you a sense of what we can do with all of this data coming. And one of my goals for this presentation is to coin this term that you are all tasked with using forevermore, and that is pseudo interferometry. Okay, and here's what I mean. So this is, you know, actual interferometry. Very, very impressive, very recent measurement of Antares, and a superbly precise measure of the angular diameter of Antares with microarcsecond precision. This can be done for handfuls of stars in the sky. It's a tour de force effort, important fundamental effort. We can effectively do the same thing with comparable precision for millions of stars without resolving their surfaces. That's the pseudo interferometry part. And so I'll just remind you of the basic idea. I mean, this is just turning the Stefan-Boltzmann equation around. If you have a good bolometric flux, and it gets even better because it depends only on the square root, and you have a temperature, in practice, where's Renbin? This is where I didn't want to go down the rabbit hole, but this is where uncertainties in models really fundamentally limit the precision of this approach, is that, you know, you depend on the temperature ultimately to the, you know, squared, and for all intents and purposes, this is the thing that limits your precision here. But as I'll show you, you can still do quite well. So we can measure an angular diameter for a star. I want to be clear, we're not resolving the stars, but this is a measurement of an angular diameter of a star through this empirical bolometric flux method, thanks to all of these catalog fluxes, Galax, the whole thing. Bolometric flux, if you have a spectrum and you have a good temperature. And so in this paper, we compared for a couple of cases, these two cases, for which there are actual interferometric measurements, how our pseudo interferometric measurements compare to the actual interferometric measurements. And the agreement is at the micro-arcsecond level. So micro-arcsecond pseudo interferometry, for those of us who are not interferometry ninjas, can work. So here is from a study that we recently did of applying this methodology to all of the then known exoplanet hosting stars in the first Gaia data release. This gives you a sense of what's possible. So for this planet host star sample, we achieve a typical precision of 2 microarcseconds in the stellar angular diameters. And now you bring in the Gaia parallax, and for the nearby stars, where the parallaxes are best, you end up with a formal precision on the radius, the physical radius of the star, of 1 or 2%. And the limiting factor in these cases is the uncertainty on the temperature. And here you see for the Gaia DR1 what the nominal, at the larger distances, you become increasingly dominated by the parallax errors. But with the Gaia DR1 parallaxes, we were already able to achieve few percent precision on the stellar radii out to like 100 parsecs. We're in the process of updating this with the Gaia DR2 parallaxes, but this is what we expect. We expect to be able to push the sample for which we can achieve a few percent radii out to a couple of kiloparsecs. Yeah.
The numbers you showed on the little table in slide 4
Yeah.
suggest that uncertainty is smaller than 1%.
Sorry. Yeah. Oh, yes. Yes, sorry. Yeah, thanks for making that clarification.
SEDs are going way out into the infrared.
Mm-hmm.
Can't you be influenced by debris disks that are irradiating the infrared?
Sure.
That could throw off your, at least the right-hand side.
Yeah, so such cases are not so common in these samples anyway. But I will say that, and I'll show you an example in a minute of where we've applied this methodology in a young cluster. And in young clusters, we definitely see cases of infrared excesses. And so, then you have to decide what to do. In those cases, what we've decided to do is to basically fit the rest of the SED and not add in the flux from presumably the circumstellar material. But certainly there are going to be, one could imagine cases where the circumstellar emission is large or even dominant. I don't know what you would do if you tried to do this with FU Orionis, for example. Yeah, well, and there are just young or eruptive stars where the circumstellar material, the emission from the circumstellar environment actually dominates over the photosphere. So we haven't tried to do that, but so now let me bring in another piece, because I just mentioned the exoplanet host sample. So if you have a precise radius for a star, and then you have something passing in front of it, there's more that you can do. So in a transiting exoplanet case, right, we observe this transit, and the transit, you can represent it as having a depth and a duration, and there's also a time that goes with the ingress and egress of the transit. And you can map these observables, these transit observables. So I've already, here's the pseudo interferometry on the stellar radius. If only we had a stellar density, we could turn the stellar radius into a stellar mass. Well, a transit basically ends up you can relate these transit parameters ultimately to the stellar density. All right? So when you have a transit, you can turn your pseudo-interferometric radius into a pseudo-interferometric mass. I'm not going to coin pseudo-interferometric mass, but I am coining pseudo-interferometric radius. And then, of course, you can relate the planet properties to the stellar properties, the radii and the masses. So this is a path to totally empirical measures of stellar and planet properties. And when we did it for the Gaia DR1 sample, again, we're in the process of updating Gaia DR2, this is what we were able to achieve formally on the precision of the stellar mass via the pseudo-interferometric stellar radius and the transit-provided stellar density, a few percent stellar mass on the best cases. And so this is where I pause and I humbly remind you that for many of us who spent decades working on fundamental masses and radii of stars, this used to have to be done 1 or 2 stars at a time in individual eclipsing binaries. And now we can weigh stars by virtue of the transit and the parallax and these very simple fundamental measures. I want to take a step aside. I think Adrian and I were talking about this no. Who was I talking about this yesterday with? Oh, yeah, Jeremy. Yeah, you and I were talking about this. Not for this system, but to make this point, which is that I haven't said much about metallicity yet, right? So I've talked about temperatures, I've talked about surface gravities, I've talked about pseudo-interferometric radii and parallaxes. It turns out that having a good measurement, ideally spectroscopic, of the stellar metallicity is really important. And for many of the systems that we're working with now, the metallicity, or our lack of knowledge thereof, turns out to be a really fundamentally limiting factor. So here is just one example of transiting planet, HATS 3. And here I'm showing you just how beautifully, by the way, the pseudo-interferometric bolometric flux and parallax method and the pseudo-interferometric mass, the surface gravity that we would infer from that method, how beautifully it agrees with the spectroscopic surface gravity. Okay, so everything's good there. But for the quoted metallicity in the literature for this system, the stars really, if you believe standard stellar evolutionary models at this level, really should be way over here. And it turns out that if the star is actually just a bit more metal poor than what was quoted in the literature, and it turns out if you dig deep, what's quoted in the literature is not very precise, then everything hangs together again. But this is just to say we need more systematic metallicity measurements of stars in order to really reap the power of this. And so that's going to mean that all sky spectroscopic surveys overlapping with these samples are going to really help kind of close the loop entirely. In the meantime, I would just say beware. You can run into these apparent big discrepancies in some cases just because you don't have a good metallicity measurement. I would say that I will make a prediction that if you were to go back and more carefully measure the metallicity of the system, you're going to get an answer more like this than this not very well determined measurement that you'll currently find in the literature.
Although, as we were discussing,
Yeah.
the star's effective temperature this hot for extremely thin surface convection zones. Even if you told me exactly what the surface metallicity was,
Yeah.
I wouldn't know how to translate that into
Yeah.
mean metal abundance in the star, which is what you need for the evolutionary.
Right. Yeah. Diffusion effects, settling.
Very small.
Yeah. Yeah. And then not to mention mixing length parameters and so on. All sorts of stuff. To kind of first order, I would say, I think we can make a lot of progress just by having good measurements of this. But Jeremy's throwing up his hands. I'm not ready to give up quite yet. Let me give you some more positive news, because this definitely works. So what about all of the stars in the sky for which one might wish that you had accurate physical parameters, but we aren't fortunate enough to have a point mass orbiting and passing in front of the star. What about just all those singleton stars out there? In the past, where we depended on eclipsing binaries, we were just left to estimate stellar masses with models and so on. I'm pretty happy about this result. So my student Fabian Bastian and I, my former student Fabian Bastian and I, and Gibor Basri and Josh Pepper, when we were playing with the Kepler data and the astroseismic sample within the original Kepler data, we came upon this really neat result, which is simply stated that you can see in the integrated light of a star in a Kepler precision light curve, you can see the granulation noise of the star. So this is what granulation looks like on a particularly nearby star. When you don't have the benefit of resolving the surface, and you just have a light curve, some number of parts per million light curve. So this is a diagram showing the overall amplitude of photometric variability in Kepler stars. So some stars have large photometric variations, but on this axis is the measure on a particular time scale of the granulation noise, and that granulation noise amplitude correlates beautifully with the stellar surface gravity. The reason for this is actually easy to understand, and that's because if you step back and you think about basic astroseismology, where you're measuring specific modes of oscillation, remember, what is it that's driving those modes of oscillation? It's the convection, right? And so like if you boil water in a pot, in principle, you can measure the ringing of the pot. What's making the pot ring? It's the boiling water inside. So this is just kind of a way of directly measuring the amplitude of the boiling water. And so this makes a fundamental measure like surface gravity accessible to a much larger set of stars than that which you can do with peak bagging astroseismology. And so here's one of the tightest correlations you'll ever see. So this is, again, for using the astroseismic sample as a calibration. This is the surface gravity you get from astroseismology. Here's the surface gravity you infer from the granulation, what we call flicker. And it's pretty darn near 1-to-1. It turns out, metallicity again, so the scatter, if you ignore metallicity, so metallicity actually has a secondary effect on the amplitude of the granulation on the convective motions for opacity reasons. If you ignore that effect, you can basically infer the surface gravities via granulation with a typical precision of about 0.1 dex. If you have a metallicity, even just a gross measure of the metallicity, and separate stars into metal poor versus metal rich, you can actually improve that precision on the surface gravity from the granulation by about a factor of 2. So we can do about 0.05 dex on surface gravity, which is competitive with even high resolution spectroscopic measures typically of surface gravities. Yeah. Yeah.
Quantity on the y-axis is measured. In both cases, you need very accurate light curves.
Yes.
But I'm guessing on the y-axis, you need quite a bit less data.
Exactly. That's right. This is just to show that the method works, but we can apply this method to a vastly larger sample of stars with lower precision light curves. So thinking ahead to tests and applying this granulation flicker method to test light curves, David Kipping and Fabian and I did an exercise where we asked, so you can infer surface gravity. Well, what else can you infer? Turns out you can also, with the same measure of granulation, infer the stellar density. And so now you can do this thing of astro density profiling, where you take the density and basically you can. So typically, when we do these transiting planet analyses, we will make some assumption about the circularity of the orbit because maybe the period is small or whatever, and include that as part of backing out the stellar density. But if you have the stellar density, you can actually turn that around and get a more accurate measure of what the planetary orbital eccentricity is. So this will actually give us a way of getting at orbital eccentricities for planets. Yeah. No, this is to show you that it also gives you density. This is empirical. Now, so that was about planet orbit eccentricities, which I think is going to be a nice byproduct. But let me come back to this idea of fundamental properties of singleton stars. Pseudo interferometric radius and log G from granulation. And we can do this between the Gaia sample. We can do radii to a few percent precision when Gaia is all said and done, and the availability of broadband fluxes in order to do bolometric fluxes, that, the whole thing that I showed you, of order 100 million stellar radii. And then for the sample that from the TESS full-frame images, we hope to be able to extract granulation measures of order 100,000 stars with pretty decently measured masses. And this is just so straightforward and empirical, and yet has the potential to unlock fundamental physical properties for lots and lots of stars. So we've started doing this with some specific interesting samples. So remember at the beginning I was telling you a story about the effects of magnetic activity on stellar properties. So my postdoc Garrett Summers and I, when the Gaia data came out, we went back and revisited the Pleiades. And we were interested in this idea of, the temperatures becoming cooler and the radii becoming larger, this radius inflation effect. Because in the Pleiades, we have a number of stars, Pleiades is relatively young, we have a number of stars that are rotating fast, they are chromospherically active, and now we have distances. We don't even have to assume a distance. We can measure the individual distances to the stars. We can pseudo-interferometrically measure the individual stellar radii. And so here what you can see for the Pleiades, and this has been scrubbed of known binaries, you can see that most of the Pleiades follow some standard isochrone here, but a number of them are clearly above. And when we then bring in the measured rotation periods of these stars, there's a pretty strong effect, not perfect, but a pretty strong correlation here, where the inflated stars, and we've measured these radii directly now, these inflated stars also happen to be the fast-spinning, presumably chromospherically active ones. And remember I told you about using lithium as an additional probe of what's happening in the interior. So if we now then take the same effect that I just showed you of radius inflation as a result of, or in correlation to rapid rotation, we can now also at the same time look at lithium. So there's this long-standing, there has been this long-standing sort of question in the literature where it's been known for a long, long time that if you look at the distribution of lithium, surface lithium abundances in the Pleiades, many of the Pleiades follow this sort of standard model of lithium depletion with solar-type internal mixing for the nominal age of the Pleiades. Many of them follow that relation, but many of them are clearly less lithium depleted than you would expect. And now, if we take the result that I just showed you of the radius inflation as a function of stellar rotation, and we make the assumption that the faster spinning stars, in order to create that radius inflation, have less efficient internal mixing, we can create a family of these solar type models as a function of the alpha mixing parameter from solar down to about 1. And remember I showed you at the beginning that we can explain the young eclipsing binaries that are chromospherically active with an internal mixing of about 1. In the Pleiades, we can fully explain now basically the full spread of surface lithium abundances with a family of solutions where we span this range of solar-like internal mixing to an alpha parameter of like 1 as a function of stellar rotation. Yeah? So we didn't look at planet accretion here at all. So this was just kind of, I don't know, kind of taking kind of the simplest sort of star-only approach of, we know that these are spinning fast. We know that their radii are larger. So now if you deposit a planet, you can pollute the surface with lithium. I haven't thought through the angular momentum. Can you spin the star up by a factor of 10? That sounds unlikely to me, but so let me skip that and end with one other thing that I'm excited about, and that is what I think is an underappreciated part of the science potential for TESS, and that is planets around very hot stars. So many of you have probably seen diagrams like this. We expect to find lots and lots of planets with TESS, and we almost always find ourselves talking about M-dwarf stars and their planets. But it turns out that, and yes, we have put the 2-minute cadence postage stamps for TESS on lots and lots of M-dwarfs. But by virtue of the full-frame images every 30 minutes, TESS is going to see, everything. And George Zhao ran a little simulation to ask, and you make some assumptions about planet occurrence rates around different kinds of stars. But the point is just to say that compared to Kepler, which by design didn't see anything hotter than about 6,000 Kelvin, we should find giant planets and maybe even Neptunes in test stars out to like 10,000 Kelvin or so. And the reason I'm excited about that is because we now know of one case, Kelt 9. This is a hot Jupiter orbiting an A0 star, beautifully characterized spectral energy distribution all the way out into the ultraviolet. We know the bolometric flux empirically. We know the properties of the orbit of the planet. We know the insolation that the planet receives. We even know specifically the amount of insolation that the planet receives in the extreme ultraviolet. Kelt 9 is the hottest planet known. It has the temperature of a K star. And but importantly, it receives many orders of magnitude more extreme ultraviolet insolation than just about any other planet known. And so now you can really, do some fun stuff. So you can ask, well, if I hit my planet with this much extreme ultraviolet light, and I do some physics, Ruth Marie Clay has worked on this problem, of photoionization and the attendant heating of the atmosphere, and so you photoionize, and that heat goes into doing some PDV work on the atmosphere, and you can estimate from Ruth's work that the atmosphere mass loss rate for Kelt 9 should be somewhere in this range. Well, this system has turned into a little nature paper factory. So more recently, there was a measurement of the H-alpha, of the hydrogen atmosphere, the hydrogen envelope around the Kelt 9 planet in Doppler, via Doppler tomography. All right. So from the basic transit discovery, we can measure the size of the planet. Here is a measure of the size of the planet specifically in hydrogen. And it turns out that in hydrogen, the planet fills its Roche radius. And so now you can kind of pin down even better what the mass loss rate is, and it agrees with our original estimate, but it's somewhere in this range. So it's pretty prodigious mass loss. And then there was another Nature paper on Kelt 9, doing the same thing, but now specifically with iron and titanium. And so from the ionization fraction in iron, you can really pin down the temperature of the planet atmosphere. Sure enough, it's consistent with a 4,000 Kelvin planet atmosphere. So all of this suggests that with JWST, we ought to be able to measure things like CO and water in transit for Kelt 9. And then we can begin addressing things like C to O ratios and putting constraints on models of planet formation and assembly and so on. So I'm excited about hot stars with TESS. I was going to say some stuff about astroseismology, but I think you all maybe know a lot about that. Let me end by just saying that up until this decade, through a lot of hard work, we had, of order this many stars for which we could really do precise benchmark stellar astrophysics and thereby do fundamental physical property measurements of the things that orbit them. And now we are entering in the next few years. This is not even prognosticating too far into the future, but like by the year 2020, this is where we ought to be on numbers. And it doesn't look so impressive in exponents, but these are massive advances. So we're going to be busy. Fundamental properties of stars, exploring a variety of stellar astrophysics questions, pinning down the properties of planets, studying the histories and pathways of planet formation and evolution. And it's because we can measure radii of stars really, really well. So thank you for your attention.
Thank you for a very nice presentation.
Thank you, David.
We have time for some questions.
Yeah, Jeremy.
Several, but I'll limit myself to one. The double brand dwarf system.
Yeah.
You suggested that maybe the inflated radius is related to magnetic field.
Yeah.
Of course, magnetic fields themselves are related to convection and rotation.
Yeah.
So maybe it's just a direct effect of rotation on convection. So my question
Oh.
is, and by the way, these rotation rates are actually quite slow compared to Lagos, right? But not compared to the convective terminal.
Right.
So how much would you have to change the mixing length between the two members of that system to explain the 10% inflated radius factor 2? Is this the system you discussed before that?
I haven't worked that out, but my intuition would be a factor of 2 sounds about right.
The convective object,
Yeah.
the velocity is just due to its contraction.
Yeah.
So if you frustrate the convection.
Yeah. So I would argue that that's almost certainly what's happening, that the mixing length alpha has been in effect dialed down from say 2 to 1. I think what you're asking is sort of what is the mechanism by which.
No, I'm just asking if you
Oh.
try to make a model,
Uh-huh.
how much do you have to tune the mixing length?
Oh, I see.
The radius. I mean, how much do you have to change it between the
Yeah.
two members of that one eclipsing volume?
Yeah.
To get both radii to agree.
Yeah. So we haven't done that. I mean, in principle, we could. We haven't done that for that system specifically, but where we have done it, right, like in the Pleiades, this factor of 2 on alpha basically gets you the full range of the radius inflation. So that's why I say that a factor of 2 sounds about right to me.
Can you measure or put a limit on absolutely gray extinction by comparing your eclipsing binary data with the diode data? Or could you do so in the near future?
On absolutely gray.
Really gray extinction.
Sorry, what's the question?
Well, from interstellar dust particles that are of large radii, say more than a few microns in diameter.
You're wondering, could we actually map out what RV is?
Well, not just RSV, but completely gray extinction. That is, extincts as uniform over all wavelengths, caused by optically thick
Uh-huh.
dust grains that are quite large in diameter.
So So that would be an RV of infinity, basically.
Or some subset.
Yeah, I mean, I think we could definitely put some limit on that. I mean, I guess maybe the way to approach it would be, I'm just thinking about this mechanically, you know, in terms of doing this kind of fitting. If I were to just crank up the RV asymptotically approaching infinity, at what point do I break the fit? Could do that.
Okay, we have time for one more question. So it's a bit of a diversion, but have you thought about what your very precise mass measurements for these large numbers of stars mean for the things like the initial mass function and stellar population models for galaxies, for instance?
Yeah. So yeah, I didn't talk about this at all, but one component of the next generation Sloan Digital Sky Survey, Sloan Digital Sky Survey 5, which we just formally kicked off on Sunday at the Chicago O'Hare Airport, and which will formally start its observing in 2020. One big component of that, of the spectroscopic program, is going to be focused investigation of a large number of star-forming regions in the Milky Way. And one of the things that we want to investigate, for example, is sort of the granularity of the IMF, by which I mean, so you could look at a few thousand stars, say in some massive star-forming regions like in Orion, and apply this methodology, and now just make a distribution of masses, and now you have an IMF. But beyond that, there's now evidence that many of these large star-forming regions are actually very substructured. So imagine constructing sub-IMFs within the same large complex, but sub-IMFs as a function of different filaments within that star-forming region. I think that there's a really interesting question to be asked.